We're now moving on to section 6.2, the Bohr model. Here we're going to describe the Bohr model of the hydrogen atom and use the Rydberg equation to calculate energies of light emitted or absorbed by hydrogen atoms. So we ended last section talking about the hydrogen atom and the Rydberg equation. So going forward in time, there were still a lot of things not being explained. So in 1913, Niels Bohr comes along and was able to convince scientists to abandon classical physics. And this is really where we start off with modern quantum mechanics. So before Bohr came along, atoms we knew consisted of tiny dense nuclei surrounded by these lighter and tinier electrons moving about the nucleus. So we talked about this before. We had the nucleus, and there's kind of these electrons just doing their thing, surrounding it, going around it, and etc. But this was incomplete because if that electron, for instance, was going in an elliptical orbit, it would be accelerating. And if we had classic electromagnetism, it would be continuously emitting electromagnetic radiation or light. But that wasn't happening. So if it's giving off energy, then it should be getting, its orbit should be getting smaller and smaller because that energy is coming off. So it's going to start moving slower until eventually it spirals into the nucleus. But again, this isn't happening. So Bohr tried to resolve this by ignoring all of this prediction, all these different predictions, and going, you know what, no, I'm going to say it's not, the hydrogen atom is not going to continuously emit light. And just also I want to stress, we are right now only focusing on the hydrogen atom. So he took the classical mechanics description of the atom and took a little pot. Into that pot, he added quantization from Planck and from Einstein, the idea that light consists of photons who have this energy proportional to frequency. And then he added some of his own assumptions that the electron orbiting the nucleus normally does not emit radiation, but it will emit or absorb photons if it moves to a different orbit. Okay, so he came up with the idea of these electrons having specific orbits around the nucleus. The amount of energy that would have to be absorbed or emitted corresponds to Planck's equation. Delta E, so final energy minus initial energy equals h nu, or hc over lambda. So these are the initial and final orbital energies. So the energies required for between two of these orbitals, or these energy levels that the electrons are at. And he also assumed only discrete values of delta E were possible, so only set whole numbers. So he came up with this expression for quantized energies. The energy is equal to negative k over n squared. And this is k is a constant, which is comprised of things like the electron mass and charge and Planck's constant. If we take this and put it in our equation for delta E from section 1, okay, we had delta E equals k times 1 over n1 squared minus 1 over n2 squared. Now we're going to set it equal to hc over lambda. And then we can go ahead and make this as 1 over lambda equals k over hc. Just kind of rearranging things a little bit, because we're putting hc over with k to make that into one big constant. And this is the Rydberg constant. Okay, so k over hc is actually equal to the R infinity Rydberg constant. So that's why it was rearranged like this. So 1 over lambda is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So he was able to rederive the Rydberg equation. Only this time with a reason for it. So this is also what we mean about energy being quantized. So these are different energy levels. Energy as an n. Okay, so when n equals 1, so the first energy level, this is the joules of energy associated with it. And then n equals 2 has a specific energy, and so on and so forth. There's no n equals 1.5. So there's nothing in this empty space. So we can only have set energy levels at these different n's. Again, there's no such thing as a n equals 1.5. It's only 1, 2, 3, 4, 5, each one of which has its own energy associated with it. So one of the laws of physics, and I know this is a big physics chapter, but physics and chemistry are friends. I had one of my old friends who used to say that, chemistry is nothing without physics, and I'd remind him, though, that without chemistry, physics wouldn't even have a purpose. Sorry, physics majors. Anyway, one thing with physics is that matter is most stable when it has the lowest possible energy, okay? Which makes sense, right? Lower energy, you're chill. Think about it like a kid. The less sugar a kid has in general, the more chill they are. They're more stable. I swear, give some of my nieces sugar, and I swear I see them vibrating. Okay, so when an electron is in its lowest energy orbit, that means n equals 1. And when we're talking about an orbit, what we're saying is we have our nucleus, and then these are our orbits. Specific energy levels around the nucleus. So that first orbit is our n equals 1. And this is called the ground state. Okay, and if we get some outside source that gives this electron enough energy, it has to be the exact amount of energy, it can move up to what's called an excited state. It can move to a different orbit, depending on the amount of energy it's given. And it has to be the exact amount of energy. And it could either go maybe from n equals 1 to n equals 3, and it's going to go straight there. Or 1 to 2. That's how this energy is jumping. Okay, so if it absorbs energy, so light is going into the atom, the photon is absorbed by the electron, it's going to move from a lower n to a higher n. So from a lower level to a higher level. And so think of this as giving a kid sugar. All right, I give my nieces some candy, get them all hyper, and they go from the relaxed watching a movie to wanting to literally run in circles around my living room. But then once that sugar wears off, just like the energy in that photon and in the electron, they relax. So if a photon is given off, the electron moves down from a higher energy n to a lower energy n. So the kids come down from that sugar high to that nice sugar crash, and that's when everyone takes a nice nap. By that point, I've already left. That's the fun thing about being the aunt, I give them sugar, get them all hyped up, and then go, oh, look at the time, I gotta go. All right. So energy, that delta E, can only be discrete values. So the photon that's absorbed or emitted can only have a discrete wavelength. Okay, so it can't be this continuous spectrum of light. It has to be a specific wavelength. And this is what explains that line spectra for the hydrogen atom. Why there's those 4 discrete lines? Because those are the specific wavelengths required to excite an electron to a higher energy state. And then have it come back down. So the light is emitted when that electron jumps up and then it chills out, and that energy that it absorbed has to go somewhere, so the atom gives it off as a photon of light. So here's an example, an energy diagram showing some of the Bohr orbits. The Borbits. I'm going to use that. I like it. Okay, so it can go from this lower energy state to straight up to one of these higher ones. And this can also happen from, for instance, this is n equals 2. It can transition there. It can fall from, these different levels. And it's going to go straight to whatever level. It's not going to go, okay, I'm going to go from 5 to 3 and then chill. No, it's going to go straight. If it wants to go from 5 to 2, that's the amount of energy that it's emitting. Okay, so you can see all these different ways that this energy can be either absorbed or emitted. So here is an example. I didn't do an example of this in section 1 because it's more important in section 2, talking about the Bohr model. So we want to know the energy in joules and the wavelength in meters of a line in the spectrum of hydrogen that represents the movement of an electron from the Bohr orbit with n equals 4 to the orbit with n equals 6. And we want to also identify what part of the electromagnetic spectrum we find this radiation. So we know that our N1 is 4 because we're starting at n equals 4. And it stops at n equals 6. So that means N2 is 6. Okay, so we're focusing on the change in energy because we want the energy in joules. So we're going to use delta E here. And we're going to go ahead and plug and chug now that we know all of our information. E equals, I'm going to put in Planck's constant, times 1 over 4 squared minus 1 over 6 squared. Excuse me. And we get our delta E of 7.566 times 10 to the negative 20th joules. So now we have our delta E. And the other part we want to know is where on the spectrum this falls. So we need to know what our wavelength is, because then we can take the wavelength and look at our spectrum of light and figure out what that corresponds with. So we also notice that our energy difference is positive, which means that a photon is being absorbed. If it was negative, then that photon is being given off. So we know that that delta E is also equal to hc over lambda. So we can go ahead and plug in for hc, and we can solve for lambda. We have delta E as well. And where was I? Oh, let me go back. Sorry. So then we get that our lambda is 2.626 times 10 to the negative 6th meters. And now we know this wavelength. We go and look at a spectrum thing, and we see that this is in the infrared portion. Oh, I missed an example here. So there is another type of energy. Oh, didn't mean to do that. Let's say keep. Let's start this over. Okay. There is another type of energy equation that I forgot to touch on. And that was that Bohr's model focused on an atom with only one electron. So it can apply to He plus, lithium 2 plus, beryllium 2 plus, etc. Okay. So these only have one electron. And then what's also happening here is there is a generalized energy expression where we have Z that is equal to the nuclear charge. Okay, the charge is basically the charge of the atom. Okay, so Hydrogen is +1. So this, this is the charge of the nucleus. So the number of protons. So +1 for hydrogen, +2 for helium, +3 for lithium. Okay, and so on. So the number of protons, basically. And so then the energy called E sub n is equal to -k times the nuclear charge squared divided by n squared. Okay, so that's just another energy equation. And then we can also calculate the size of the orbits for these atoms. Okay, so this is the radius, okay, of the atom is equal to n squared divided by the nuclear charge times alpha naught. Okay, and this is called the Bohr, and this is the Bohr radius. And it is equal, alpha naught is equal to 5.292 times 10 to the -11th meters. So this gives you a way of, this is just another example of an energy equation and the radius, and to be able to find the radius of a Bohr orbit, of a Borbit. And so then, for instance, if we want to find the energy of an electron, we're told we have n equals 3. I'm going to go ahead and erase this upper part. Or, you know what, I'm just going to start over. Okay, so we're told we have n equals 3. And we want the calculated energy in joules. And we are looking at a hydrogen atom. So we know that our energy is equal to -kz squared over n squared. Okay, and we know that for hydrogen, z, that is the nuclear charge, is equal to 1. So this equals -k is 2.179 times 10 to the -18th joules times 1 squared divided by n is 3 squared. So you get -2.421 times 10 to the -19th joules. All right, so I just wanted to show that quick example and that equation as well. So there are some limitations to the Bohr model. So Bohr could not take his theory for helium, for the helium atom. For helium-2 plus, with only 1 electron, okay, but once you get more than 1 electron, it kind of falls apart. His model does not account for interactions that the electrons may have in each other when you have, again, atoms with more than 1 electron. So his model was really flawed because even though it paved the way for our quantum mechanics, it still was based in the classical mechanic notion of these precise orbits of electrons. So at least we've gone away from the elliptical orbits kind of going wherever to now we have round, circular, set orbits, but we're still not there yet. And that's where quantum theory is going to come into play, and we're going to talk about that and introduce it in the next section, section 6.3. But one thing that the Bohr model does do that is very important is it introduces us to the thought that the energies of electrons, or energy levels, are quantized, described by quantum numbers. So these integer numbers that have only specific allowed values to characterize how the electrons are arranged in an atom. So they can only be at these specific numbers. It also helped us see that an electron's energy increases with increasing distance from the nucleus. Okay, so the amount of energy increases as we get farther from the nucleus. And that these lines on the spectra come from these quantized energies. So moving forward, Bohr actually did win a Nobel Prize in Physics for his contributions. And because of his work, it became clear that the classical theories work great in the macroscopic world, but they kind of suck for the microscopic domain of atoms and molecules. So then we finally came up with the proper quantum mechanic model to supersede classical mechanics.